Once we are comfortable recognizing and using different functions, the next step is to learn how to analyze these functions. For example, we can analyze the functions to determine their rate of change. This type of analysis is referred to as differential calculus. The rate of change or derivative can be used to determine quantities such as the slope. If we repeat this process, we may obtain the rate of change of the derivative, which can enable us to determine local points of maximum minima or even inflection. But first, let's look at how we can determine the rate of change of a function. The first steps is to approximate the rate of change by using the slope of the function. The slope can be determined by taking any two values of input, such as x1 and x2, and then determining the corresponding outputs, such as y1 and y2. The difference in y divided by the difference in the x gives us the slope, which also turns out to be the tan of the angle. In terms of notation, we can use the delta symbols, which refer to an increment in some value. And we go from f of x to fx plus delta x. y2 minus y1 is then the difference between these 2 points in the function, and we divide it by delta x in order to get the rate of change of y with x. If we reduce this increment size such that delta x goes to 0, we can get a much more accurate determination of the rate of change. And this is referred to as the instantaneous rate of change of the function, which we can notate as df over dx. For example, if we take a function of f of x is equal to 3x squared plus 2, we can perform an analysis of the instantaneous rate of change. First, we determine y2, or f of x plus delta x, and we introduce delta x into the x variable, so we get x plus delta x all to be squared. Next, we introduce y1, or f of x. So now we've got f of x plus delta x minus f of x, and this is what we can call delta f. If we divide it by delta x, now we've got delta f over delta x, and if we put delta x to 0, we simply end up with 6x. Notice how the instantaneous rate of change is notated now as df over dx, and this is indeed another function, a new function called f dash of x. In terms of notation, you will see that there's a variety of ways to write the instantaneous rate of change, either in terms of df dx, f dash of x, y dash, and even dy dx. If we visualize this new function, we can see that it is a linear function. And this linear function can tell us the rate of change of the initial function at any value of x. For example, the rate of change at x equal to 0.6 is 3.6. Notice that we have initially a second degree polynomial, which has been mapped onto a first degree polynomial. In general, differentiation takes x to the power of n and maps it to nx to the power of n minus 1. This type of differentiation is referred to as differentiation from first principles, and you can apply it to any function. However, once we determine what the typical result is for generic functions, we can instead adapt shorthand rules, such as the derivative of x to the n is equal to nx to the power of n minus 1. Next, let's review these common rules of differentiation. Again, once we determine the derivatives for standard functions, we can adapt these shorthand rules such that we don't need to show the full differentiation by first principles method. Instead, we can adapt quicker shorthand methods by using common rules for common standard functions. The first type, of course, is the constant, and the rate of change of a constant is 0. Next, for power law functions, like in the previous example, the derivative becomes nx to the power of n minus 1. The exponential function has a derivative of a to the x over natural log of x. If it's an exponential to the base e, the derivative of this function is quite special, and it is exactly the function itself. So the rate of change of e to the x is the value e to the x. The derivative of any log to the base a is 1 over x natural log a, and the derivative of natural log is 1 over x. Next, we've got the basic trigonometry functions. Cosine of x, the derivative is minus sine of x. And for sine of x, the derivative is cosine of x. Finally, the derivative of tan x is 1 over cosine to the power of 2x, or cosine squared x. Similarly, the hyperbolic functions, which we looked at in the previous lecture, have similar derivatives, such that hyperbolic cosine x has a rate of change equal to the hyperbolic sine x function, and vice versa. Finally, hyperbolic tan has a rate of change of 1 over hyperbolic cosine squared x. So these derivatives are very similar between the trigonometry and the hyperbolic functions. While determining the derivatives of these standard functions is relatively straightforward, next we will look at situations where we wish to analyze combinations of functions. And here we will use standard notation for different functions, such as f of x and g of x. Again, we can develop some shorthand rules to deal with such scenarios. In the first case, we've got two functions that are added together, and we wish to get to the derivative. Here, the derivative is simply the sum of the individual derivatives, f dash plus g dash. Next, if we are multiplying functions and we wish to get the derivative of both of them together multiplied, we use the product rule, and it's equal to f g dash plus g f dash. If we are dividing two functions, we can use the quotient rule. We can determine the derivative by calculating f dash g minus f g dash, all divided by g squared. And finally, if we have a composite function, we can use what's referred to as a chain rule. And the chain rule is frequently used, and it's probably best shown through an example. Here we have a function, or indeed two functions. We've got 5x to the power of 3 minus 7, all of it to the power of 4. So the first function is to the power of 4, and the embedded function is g, which is 5x cubed minus 7. Using the chain rule, we first get the derivative of f, which of course is 4 bracket everything to the power of 3. And then we get the derivative of the inner component, g, and that's simply 15x squared. We combine them together using the chain rule, and we get 60x squared multiplied by 5x cubed minus 7, all to be cubed. And again, visualizing this result enables us to compare the initial function and its rate of change, or the derivative function. Notice here that the red line, the derivative, is all negative. So the initial function in blue is decreasing with x until it starts to flatten out towards 1, where the rate of change approaches 0. When we are dealing with functions that are not explicitly defined in terms of x, i.e. when we're dealing with implicit functions, such as the equation of the unit circle, we would nonetheless wish to analyze these functions to determine the derivative. There are two relatively simple methods for differentiating implicit functions. First, we can simply solve the equation for y and then differentiate this. Here we've differentiated the function after we solve for y, and y is equal to 1 minus x squared all to the power of a half. If this now is our explicit function, we can simply get the derivative, and because there are two components, it's a compound function, we can use the chain rule. One of the functions is the 1 minus x squared, and the second is everything to the power of a half. Using the chain rule, we determine the derivative of the individual components and then multiply them against each other. We determine that the derivative is x over 1 minus x squared to the power of a half, which is simply y. So the result is x over y, or minus x over y. Again, visualizing the derivative can be very, very useful to develop an intuitive feel for the differentiation. According to the derivative function, we expect the derivative to go to infinity as x approaches 1 or minus 1. And we expect, based on the simple equation, the derivative goes to 0 near x is equal to 0. Alternatively, we can perform a direct differentiation of the implicit function without first solving for y. To do so, we assume that the variable y is indeed a function, and then we differentiate this y function using the chain rule, since it's y to the power of 2. Hence, the variable x squared differentiates as 2x, whereas the function y to the power of 2 differentiates as 2y y dash. With the derivative of 1 being 0, we can then solve for the derivative function y dash, and doing so, the 2's cancel out, and we have y dash is equal to minus x over y, exactly as we had with the previous method. Next, let's look at how we can perform differentiation with parametric functions. Previously, we described parametric equations where variables such as x and y are dependent on some other variable or parameter, such as t. The example we'll use here is the kinematic equations of motion, where we can predict the position x as a function of time, and also the height as a function of time, y. If we are interested in determining the derivative of y with respect to x, we must perform a parametric differentiation. This is relatively straightforward. First, we determine the derivatives of y and x with respect to t. Next, we can easily determine the overall derivative of y with respect to x by dividing the two previous results. If we set some initial conditions for the velocities and acceleration, we can easily visualize these derivative functions and perhaps get a deeper intuitive understanding. Using initial velocities in x and y direction to be 15 meters per second and the acceleration to be only in the y direction pointing downwards at 9.81 meters per second, we can see that the resulting motion in y follows the classic parabolic trajectory. The velocity in the x direction is constant, given by dx dt, as is the velocity in the y direction. This velocity is initially positive. It goes negative as the projectile starts falling back towards the ground, and the green line illustrates the derivative of height with respect to horizontal range. This final parametric derivative enables the relative change in position to be determined by dy dx. This quantity is dimensionless and is initially equal to 1 and goes to 0 near 1.5 seconds as the object reaches its maximum height, where dy dt goes to 0. So far, we have determined the rate of change of a function. The new derivative function can be then analyzed for its own rate of change. That is, we can determine the second derivative. This process can be repeated as long as the derivatives are differentiable functions. These higher functions are very, very useful in that we can use them to analyze the original function and determine some interesting features. If we start with a cubic polynomial, as indicated by this black curve, this function is 5x cubed minus 6. If we repeatedly differentiate this function and its derivatives, we reduce the order of the polynomial first to a second order, then to a linear, and then to a constant value of 30, after which point it will have 0 rate of change and there are no more higher derivatives. In terms of notation, the higher derivatives can be noted using additional dashes or indeed using powers such as d squared y dx squared for the second derivative. These higher derivative functions are very useful in analyzing the original function, such as determining features of local maxima, local minima, points of inflection. These enable us to potentially sketch the curve of the function, and later we will also use higher derivatives to approximate the original function using the Taylor series approach. The first derivative of a function evaluated at some point provides a measure of the instantaneous rate of change of the function at that point. When this is equal to 0, we have what is called a stationary point. Think of the derivative of distance with respect to time, that is velocity. When this derivative is 0, the velocity is 0, and something with 0 velocity is stationary. Some stationary points are local maxima or minima, while others are horizontal points of inflection. You may also see these referred to as critical points. Typically, we want to perform some analytical method in order to determine where these points are in the function. This method uses initially the first derivative to determine where the stationary points are located. Next, we check the sign of the second derivative at these stationary points. And if the second derivative at this point is negative, the point is a local maxima. And if the second derivative at this point is positive, we have a local minima. And if the second derivative changes sign around the stationary point, we have a point of inflection. A point of inflection is where the function curve crosses its own tangent, and this indicates a change in concavity. Here in this illustration, we can look at where the curve is firstly convex, where it's colored blue, where it's concave, it is green, and where we have a change of concavity, we have a color of red. In this simple example, the points of inflection coincide with where the curve crosses the x-axis, but this is not always the case. Most functions will not have this symmetry around the x-axis, and hence the points of inflection could be far removed. To illustrate this, let's take an example of some polynomial function, and we'll determine where its maxima and minima are, and we'll also determine where any points of inflection are. This polynomial function is x cubed minus x squared minus 6x plus 3. First, we determine the first derivative in order to locate the stationary points. These points are where the first derivative is equal to 0. Since we have a quadratic equation for the first derivative, we can solve this using the roots of the quadratic equation formula. Here we determine that they are two stationary points at minus 1.12 and 1.79. Are these points maxima or minima? For that, we need to use the second derivative to tell us that the point at minus 1.12 yields a negative number, and hence this is a local maxima at minus 1.12, whereas the point at 1.79 yields a positive value of the second derivative, and that is a local minima at x is equal to 1.79. Finally, we can determine if there are any points of inflection by looking where the second derivative changes sign. To do so, we can determine where the second derivative is 0, and from there we can determine where the second derivative crosses the x-axis, i.e. when it changes sign. Solving the equation tells us that the second derivative crosses the x-axis at x is equal to 1 over 3. To ensure that this is indeed a real change of sign, we have to perform a short test, and we do so by choosing a point just before and just after the point in question at 1 over 3. In doing so, I've chosen 0.3 and 0.36, and I can see indeed there is a sign change in the second derivative around this point, and hence we can confirm that we have a point of inflection at x is equal to 1 over 3. Next, let's visualize the initial function, which we call y. And already we can see there is a maximum and a minimum located quite obviously, and we've determined the locations of those. We've also located the location of the point of inflection, where the initial function changes concavity. If we visualize the first and second derivative of the original function, we can see that the blue curve tells us where we have stationary points by looking at where the blue curve intersects the x-axis. And we can confirm that the stationary points are at minus 1.12 and 1.79. Notice the red curve, the second derivative, goes to 0 at x is equal to 1 over 3. We can see exactly that it does change sign from negative to positive, and this signifies our point of inflection. Finally, let's summarize the main learning outcomes of this lecture. Firstly, we should be able to differentiate standard functions as well as implicit functions and parametric functions. We should also be able to differentiate combinations of functions. And lastly, we should be able to determine the critical points of a function by analyzing its higher derivatives. As always, this is just a starting point. Please continue your studies using your textbook and practice many sample problems.